Okay, let's do some one-dimensional momentum conservation examples. Then we'll do some two-dimensional momentum conservation examples. One dimension, so we don't have to worry too much about vectors. Okay, so let's say that we have a car, mass 900 kilograms, and let's say it's moving. It's just slowly creeping up to an intersection, and let's say that the speed of the car, or the velocity of the car actually, is 9 meters per second in the forward direction, mass of the car. And let's say there's a milk truck. There's no such thing as milk trucks anymore, are there? Well, I guess there are. They deliver milk to supermarkets. But there's a milk truck, and let's say that the truck has a mass of 1,000 kilograms. Oh, did I say 900? I meant 500. Sorry, 500 kilograms. 1,000 kilograms, meaning I want it to be bigger than the car. It is stopped at a traffic light. V truck is equal to 0. Let's say that the car is not paying any attention, and it crushes into the truck. And what happens is it sticks to the truck, and they go off into the intersection. Immediately after the collision, what is the speed of the car-truck combination, the stuck-together car-truck combination? Keep in mind that they are stuck together. Okay, and I say immediately after the collision because what happens when you get an automobile accident or something like this happens is that after the collision, the two may slide off, but they're going to come to a stop because of the external force of friction. But we can talk about a collision as happening instantaneously. While collisions are not really instantaneous, we can approximate, and we will approximate in this class, that collisions, unless you're otherwise told, are instantaneous. And what that means is that during the collision, there are no external forces on the system. And if there are no external forces during the collision, that means that just during the collision, just for the moment between when the car hits the truck and immediately after, just for that moment, momentum is conserved. After that, momentum is not conserved, right? Because slide along the road or drive along whatever, they'll slide along the road and the external force of friction will bring them to a stop. But immediately during the collision, we can assume that momentum, the total momentum of the system, is conserved. We say momentum is conserved for the collision. It's not conserved before the collision necessarily. It's not conserved after the collision, but it's conserved from immediately before the collision to immediately after the collision. That's what we mean by momentum is conserved for the collision. So, how do we solve this problem? We can say that for the time immediately before the collision to the time immediately after the collision, the momentum is conserved. That means that the total momentum before the collision is equal to the total momentum after the collision. So the total momentum is the momentum of the car. Remember, these are vectors, plus the momentum of the truck before the collision. And we say that that is equal to the momentum of the car plus the momentum of the truck after the collision. So we have to evaluate these in order to figure out what is the speed of the car or truck after the collision. It is a vector. So because it's a vector, if we want to evaluate this and this, we need to choose a positive direction. Whenever we have vectors, we have to choose positive directions. We didn't do that when we did energy conservation because energy conservation is not a vector equation, but this is a vector. So, and I'm here flailing my arms, you can't see me. Okay, so we need to choose a positive direction. So I'm gonna just remember that the car is traveling in this direction, the truck is sitting still after the collision. So the situation we have, before the collision, the car and the truck are independent, they have their own velocities. After the collision, they're stuck together. And I said that they stick together, and they've got the same velocity. So that's one thing you got to recognize, is that if they're stuck together, they have the same velocity. So V car after and V truck after are equal to each other. Okay, so choose positive direction. It seems reasonable to say that this is the plus X direction because everything's moving to the right. You can choose whatever direction you want as the positive direction. So therefore, we can write that the momentum of the car is equal to the mass of the car times the velocity of the car, which is equal to the mass of the car, 500 kilograms, times the velocity of the car. Velocity, not speed. the velocity of the car is 9 meters per second, I believe. It was, 9 meters per second in the x direction. That's the momentum of the car before the collision. The momentum, and this is B4. And the momentum of the truck before the collision is equal to the mass of the truck times the velocity of the truck before the collision. And that is equal to the mass of the truck, 1,000 kilograms, times the velocity of the truck, 0, which equals 0. After the collision, we've got momentum of the car equals the mass of the car times the velocity of the car after the collision. We often just call that v car prime. Prime means after, unprime means before, but I'll just keep using the subscript v car after, which v car after is unknown, but m car is 500 kilograms, and v car after is unknown. You've got to get used to just using letters if you don't know numbers. And that's the momentum of the car after the collision. And the momentum of the truck after the collision, it is now moving because it is moving with the car. And that is the mass of the truck times the velocity of the truck after the collision, which is equal to 1,000 kilograms times v truck after. And we can then we can do the big equation in the middle here and write that down. So what we've got is P car plus P truck before, we got to add up these, equals P car plus P truck after, add up those. We get when we sum the momentum before equals the momentum after. And then we got to recognize, these two are the same because it's stuck together. So we can just call that V after because they're the same. And so and let's multiply some numbers, 4,500 kilogram meters per second in the x direction. Got to carry your directions and your signs. Equals, these are the same, so I can factor out a 500 and 1,000, so that's 1,500 kilograms times V after. Keep the vectors, and so therefore solve for V after. V after is equal to, divide both sides by 1,500 kilograms. We get 3 meters per second. Carry your units, I. That's the velocity of the pair immediately after the collision. So we can go back and say, they're going 3 meters per second immediately after the collision. Sure, they slide to a stop, but that's their velocity immediately after the collision. Notice again, I'm going to say it again, it's a vector equation. You've got to carry the vector signs. You've also got to recognize that if they stick together, they've got the same velocity. This is what's called a sticking collision or an inelastic collision. It doesn't bounce, it's inelastic, they don't bounce off of each other. We'll talk about the difference between sticking collisions and bouncing collisions later, but for now, just letting you know, this is called a sticking collision, where they stick together, or an inelastic collision, where they don't bounce off of each other. We got to be careful, because this is both sticking and inelastic, but they don't necessarily mean the same thing. Sticking means that they stick together, which these did. Inelastic actually means that they lose energy in the collision, which we haven't proven at all. And we'll just wait until we talk about that later. But it doesn't mean that they necessarily stick. So sticking does mean inelastic, but inelastic doesn't necessarily mean sticking. Again, what inelastic actually means is that they lose energy in the collision. That energy, by the way, is lost as heat in the collision, right? The two cars heat up. But that comes later. Part B, and say, okay, so they stick together. They have a velocity after the collision of 3 meters per second. How far do they slide? So I could have asked from the beginning, two cars hit each other, how far do they slide? But I just did the intermediate part. How far do they slide? So we are assuming that after they hit, they're going to slide as opposed to roll. If they roll, they're definitely going to go further. And basically, and actually this is sort of a good concept for you to know, if they roll to a stop, if their tires roll and their brakes aren't locked, then they will. Then it's essentially, effectively, just the friction is much lower, and you have what's called rolling friction instead of kinetic friction, and the coefficients of rolling friction are much lower than the coefficients of kinetic friction. So it would just be a different coefficient of friction if they rolled to a stop instead of slide to a stop. But let's just assume that their brakes lock and they slide to a stop. So this is no longer a momentum conservation question. This is two vehicles are stuck together going 3 meters per second, and they slide and they come to a stop because of friction. So this is a Newton's second law problem, or it's a work energy problem, right? So here. Let me set it up again. Immediately after the collision, they have a velocity of 3 meters per second. They slide to a stop, a distance s, let's say. We could have called it x because we know that this is the x direction. And the final velocity is 0 of that combination. How far do they go? Well, this you could just do this as a Newton's second law problem, or we can do it as a work energy problem. It's actually a little easier, I think, to do work energy. We can say that the total work done on the system while between these two positions, right? Add in there that's the collision point was right before it had 3 meters per second velocity. The collision is done. Okay, so the total work done from after the collision to when it comes to a stop is equal to the change in kinetic energy of the system. And the total work done is done by, think about a free body diagram of the car-truck combination. A free body diagram, that's supposed to be the car-truck combination. There's normal force up, there's gravitational force down, and there's a frictional force in that direction. FFK. I meant to say FFK. Okay. The frictional force is slowing it down. That's a free body diagram. So the total work done, normal force does no work in this case. Gravitational force does no work because it's not on a hill. So the total work done is the work done by the frictional force, and that is equal to the change in kinetic energy. So therefore, the work done by the frictional force is, we can fill in the left-hand side and then fill in the right-hand side. So the left-hand side first. Work done by the frictional force is the magnitude of the frictional force. The magnitude of the frictional force, FFK, times the magnitude of the displacement, S, times the cosine of the angle between the frictional force and the displacement. The frictional force is to the left, S is to the right, so this is 180 degrees. S is our unknown, and FFK we can evaluate as mu K Fn. Fn we know is mg because it is not accelerating up or down, so it's mu K mg. Okay, that's just the left-hand side, equals the change in kinetic energy, 1/2 mv final squared minus 1/2 mv initial squared, the change in kinetic energy. Now, which m is this? That m is the mass of the combination, right? It's the truck plus car. So this is the mass of the truck plus the mass of the car. V final is 0 because it comes to a stop. V initial is 3 meters per second because that's what it had before it started sliding. So I've just quickly written down total work equals change in kinetic energy, identified all my variables just by pointing at them in the equation rather than writing everything down on the side, just because this is the kind of problem we've done before. And so we can go ahead and plug in, therefore, mu K mg s cosine theta is equal to, I'm just going to write down everything still in terms of letters, just taking out all the zeros that we know of. M V initial squared. I don't know if that was useful. That step was useful. Again, I didn't say, but I hope it's clear that the whole problem is for the car-truck combination, so that the m's are the same. That's important to notice because sometimes we have situations where we're talking about two different masses, but the m's are the same. So I'm going to go ahead and never mind that arrow, but the m's are the same, and say mu k mgs cosine theta, mu k mgs cosine theta is equal to minus 1/2 mv initial squared, where mu k is 0.5, m is the total mass of the combination, 1,500 kilograms. Oh wait, but that cancels. That cancels. Ooh, it's always better to cancel so we don't mess up our math. So we don't mess up in our calculator. So those cancel because they're the same mass. G is 9.8 meters per second squared. S is the unknown thing we want to know. Theta is 180 degrees. Minus 1/2 V initial is positive 3 meters per second squared. Okay, Carried my units, make sure the units make sense, and make sure the signs make sense, right? Carried my signs, paid attention to the signs. There was a negative sign here. And you might say, oh, but there's no negative sign on the left, but cosine 180 is negative. So we got negative 0, or here, hold on a second, let me just do it this way. That 0.5 times 9.8, well, this is negative 0.5 times 9.8. We can just do that all at once. So we've got minus 4.9 meters per second squared times s equals 3 squared is 9 meters squared per second squared times minus 1/2 is minus 4.5 meters squared per second squared. Do the units make sense? Well, no, we're not done yet. Let's solve for s. Therefore, s is equal to minus 4.5 meters squared per second squared over minus 4.9 meters per second squared, which is equal to 0.92 positive because the minus signs cancel, and the units end up being meters, 0.92 meters. So they slide only a meter before they come to a stop. So they don't slide very far at all, so they hardly slide into the intersection, so they stay pretty safe. It's only a meter. Okay. Conserved momentum during the collision. We conserved momentum during the collision, and then after the collision, is momentum conserved? The answer is no, it's not, because the velocity changes while the mass doesn't. Momentum is not conserved because there is an external force of friction, and that external force of friction slows them down, takes energy away from the system, and so we can use the work energy theorem after the collision to say what happens, and they slide 0.92 meters. Okay, so that's a momentum conservation problem and an energy conservation problem. Okay, done with that. Let's move on to another example.